So today I want to start talking about the formal languages more specifically. First, a few definitions. An alphabet is a finite set of symbols. A string is a concatenation of these symbols into a sequence, where order, of course, matters. A language is a possibly infinite set of strings. Now, it's a very general definition, so a lot of different sets could be languages. But it's a set of strings, that's its type. A string length is the number of characters in it. The empty string is a unique string that has length 0, right? It's also the identity element with respect to concatenation, as you see in these examples on the right-hand side in green. String concatenation simply is a juxtaposition of the two strings side by side, and order matters. Language concatenation is the extension of string concatenation to languages, where you concatenate every pair of strings from the two languages in every possible combination, all of them. So for example, 1, 2 concatenated to A, B, and so on is 1A, 2A, 1B, 2B, and everything else that might be in these two sets. String exponentiation generalizes concatenation to any number of concatenations. So W to the K is doubly concatenated to itself K times. So concatenation among strings is sort of the analog of multiplication of numbers or integers, right? And W to the 0 is the empty string. It's the identity element with respect to concatenation. Language exponentiation is the extension of exponentiation to languages, where you concatenate the language to itself that many times, right? So you apply this definition of language concatenation, not just one language to another, but the language to itself, and a lot of times, up to the exponent denoted by k. So inductively, L times L, L concatenated to L is L squared, L to the k is L concatenated to L to the k minus 1. That's the inductive way of defining concatenation or exponentiation of a language. And the language exponentiated to the 0 is the empty string taken as a language. So it's a language containing the single string, namely the empty string. Any questions about any of that? So that's quickly just a bunch of definitions that will enable us to derive a lot of interesting results as a consequence. A few more definitions. String reversal is writing the string backwards. So you reverse the order. You can reverse a language by reversing each and every one of its strings. And you can union and intersect languages, and that simply is the set definition of union and intersection, because languages, after all, are sets. So you can do to them whatever you can do to sets, including union and intersection operations. You can take the difference of two sets, i.e. the difference of two languages in this case. So it's every string that's in the first and not in the second is a string, therefore, in the difference of two languages. And you can take the Kleen closure of a language, which is all the powers of the language beginning with 0. So it's L to the 0, union L to the 1, union L squared, union N cubed, and so on. And L plus is all finite powers of the language other than 0. So L star and L plus are quite similar. They only differ in the first term. And a Kleen closure is another way of saying L star. So all finite strings over sigma, for example, could be denoted as sigma star, right? All ways of concatenating strings from a finite alphabet, sigma. So in this course, alphabets will always be finite. You don't have to worry about infinite alphabets or even infinite strings. In fact, sigma star doesn't contain any infinite strings anyway, right? Because it's all finite powers, and the string from every component of this infinite union is still finite, right? L to the 100 still gives you strings of only size 100, and L to the Google will only give you strings of size Google, and so on. So infinite strings will not come from any of the components of the Kleen closure, and therefore will not be in the Kleen closure, infinite strings. So don't make that mistakes of thinking that some strings are infinite. They're not. Not if, you know, and in fact, in cases like this, we have infinite union of powers. Just keep in mind that the powers never get to infinity. The power gets arbitrarily large, commensurate with every integer, but no integer is infinite, right? The totality of the integers is an infinite set, but any integer itself is not infinity, and it's not an infinite quantity. So keep that in mind. That will come back to haunt you probably on a number of occasions, that misconception. The complementation of a language is simply everything that's not in the language. That's sigma star minus the language. You have to be careful what you're complementing with respect to, right? So if I say the complement of the prime numbers, right, that's the composite numbers, right? The numbers which are not prime. But you can say also, well, my right shoe is in the complement of the prime numbers because it's not a prime number. Certainly my right shoe is not a prime number. It's not even a number to begin with. And therefore you might say, well, then it must be in a complement. Well, no, because we're complementing with respect to some fixed known universe, in this case integers, not just with some arbitrary collections. So just be careful what you're complementing with respect to here, okay? You can easily prove that if you clean close it twice, it's the same as just doing it once. So L star star is the same as L star. That's not a definition, it's a consequence. It's a corollary of the definitions, or a theorem, if you will. So one way to prove equality of sets is you show that each one is a subset of the other. So for example, to show this, first show that L star is a subset of L star star, and conversely that L star star is a subset of L star. So if two sets A and B, each one is a subset of the other, they must be equal to each other. Okay, so typically that's a proof technique to show that two sets are the same, and in case of languages, that comes in very handy as a strategy. You can also show that L plus is L star. The trivial language is the unique language containing the empty string. Its size is 1. The empty language is different than a trivial language. Its size is 0. It's the empty set. So don't confuse those two. Sigma star is countable. Its cardinality is the same as that of the natural numbers. How would you count sigma star? How would you map sigma star to the natural numbers? At this point, it should be a few seconds. Not very long process of thinking about it. What's that? Dovetailing, good. That's a one-word answer. Can somebody expand that to a whole sentence? What does it mean by dovetailing? How would you dovetail through strings and sigma star, numbering them each in turn?
Sort all the strings by length.
Yeah, sort them by length, within length by dictionary order, and just number them. Good. So I'm glad you're quick about this. Now, 2 to the sigma star, the power set of sigma star is uncountable. You can show that by diagonalization. I'll leave it to use an exercise to argue why the number of subsets of sigma star is not countable anymore. It's certainly infinite, but it's more infinite than a countable infinity. Okay, any questions about any of this so far? So far we just had some definitions, a couple of theorems, and then things will get deeper as we go forward.
Quick question.
Yeah.
So some of that stuff I remember from like discrete math, but
Good.
like the sets, but some of it I don't. So like what is what area would I want to focus on if I wanted to
Okay.
cover this a little bit more detail? Just if I
Good question. One source is chapter 0 in the book. The first, 20 or 12 or 20 so pages in the book. Source 2, I have a handout on the class website that's basic definitions and concepts. All these things are defined. It's like one big glossary. You've probably seen it in the algorithms course from last semester. That still covers, the sigma star and the clean closure and all these kind of concepts, one-to-one correspondences, dovetailing, diagonalization. So that glossary in a web page, on the class web page, is a great place to go to for all the definitions in one place.
So just would this have been something I would have seen in discrete math or a class like that and just don't remember, or is it not really part of discrete math? It's more.
Some of it you would have seen, like union, intersection, set operators and that kind of thing, and complementation of a, but things like clean closure you may or may not have seen, depending where you took it and who taught it. But countabilities in countable and uncountable infinities and Cantor stuff, like we covered last time, chances are it wasn't in a typical discrete math course, because it gets pretty technical, and most of the sets there are either finite or countable, but not uncountable. There's a reason why they call it discrete math as opposed to continuous math, right? So when you talk about discrete, either it's a finite number of things or a countable number of things in case it's infinite, but not uncountable, and so you don't worry so much about cardinalities. Here we do. Cardinalities will play a big role in our stuff, including in proofs and arguments and whatnot. Any other thoughts or questions? Yeah.
I'm not so sure about the relationship between trivial language and empty.
Okay, so the empty language is the language equal to the empty set. So it's a set containing nothing. It's just brace with nothing inside. The trivial language is a language containing one string, not 0 strings. One string, and that string equals the empty string. So the empty language, its size is 0. The trivial language, its size is 1. This contains a string, this doesn't. And the string that this contains happens to be the empty string specifically. So the empty language is the identity operator with respect to union. It's the identity element with respect to union. You take any set, union that with the empty set, you get that set back identically. Right? For example, with addition, the identity element is what? The arithmetic addition. 0. With multiplication? 1. With matrix multiplication? Identity matrix. With union? The empty set. With concatenation of languages? With concatenation of strings first? Empty string is the identity element. Right? Empty string concatenated to anything is that thing back, unchanged. With respect to language concatenation, the identity element is the trivial language. Okay. So keep in mind, any operation, most operations have an identity element of some kind. Then when you apply that operation, the identity element plus some other element, you get that other element back, unchanged. So we just went through half a dozen examples of that. Okay. Any other thoughts or questions? The definitions are very important because everything will build on these definitions. You know, there's not that many of them. You know, we just saw, you know, a dozen or so definitions, but things will build very heavily on that. Yeah.
Yeah, just want to confirm. When we say dovetailing, we mean the way when we map natural number with rational number, right?
Yes. So it's that dovetailing, but dovetailing can be disguised as other things too. So for example, if I take all the strings in sigma star and I number them 1, 2, 3, 4, and arrange them by size, and within size by lexicographic order. So the shortest string first will be epsilon, then the next largest string will be A, then B, then AA, AB, AA, you know, BB, AAA, AAB, and so on, all by size. There's only a finite number of strings of any given fixed size. Write them all down, then go to the next size, write the next batch down of slightly larger size, and so on. Then number them. That's dovetailing too. So don't confuse dovetailing with these zigzag line that you saw in that, you know, square matrix. That, yeah, this was dovetailing when you did the rational numbers, you know, mapped to natural numbers or integers. But the dovetailing concept is not restricted to this serpentine snaking line. It could take algebraic forms or analytic forms or just forms that have to do with either an equation or just a description, like we just did for sigma star. That's also dovetailing. Dovetailing is a systematic way to hit them all with numbers, however you want to do it. You know, it's not just this picture here. This picture is a special case of dovetailing. It's a way of arranging a set in such a way that you can easily map it to the natural numbers. Okay, I would be reluctant to use the word sorting because sorting has a different connotation in algorithms and usually it pertains to finite sets. But yeah, it's a way of ordering, or if you will, sorting. Although you have to be careful when you talk about sorting infinite sets. You know, it's a bit of a slippery slope, but let's just say ordering instead of sorting. Yeah. Okay. Any other thoughts? And we'll run into other ways of sorting or ordering different sets, not necessarily with a pretty picture like this, but algebraic ways. So for example, even the fractions, instead of using this technique to order the fractions, what we could have done is order the fractions in a way that has maximum numerator or denominator bounded by a certain value. So write all the fractions down whose numerator or denominator in maximum absolute value doesn't exceed 1. So 0 over 1, 1 over 1, and that's about it. So there's a couple of fractions. Now go to 2. If you go to 2, you have 0 over 2 is still 0, so we're not going to write it again. 2 over 1, 2 over 2 is 1, or 1 over 2. So you get a couple more fractions, and so on. You get to 3, you get a few more, and so on. And now just number them. we'll call this one 1, 2, 3, 4. That's dovetailing also, except it's a different dovetailing than this. Because here we don't have a nice square table, but we are getting all of them. All the fractions will eventually, and you can of course add the pluses or the minuses, right? So you can say minus 1 over 1. So whenever you have the pluses, just write the minuses too. Minus 2 over 1, minus 1 over 2. So just to hit the negatives, just in case, because those are rationals too. And now, that's a way to order the rational numbers in a dovetailing fashion, different than this dovetailing fashion. This is easier to see. But so this is a geometric dovetailing. This is an arithmetic or algebraic dovetailing. Okay, but they're both dovetailing technique. Good question. Any other thoughts or questions? So in the book, we're entering chapter 1. We're going to talk about regular languages, and that's on page 34, 35. So all of you should be reading the first chapter of the book at this point pretty regularly. All right, so finite automata. Finite automata is a computation model. It's an abstract machine that's basically a set of states and a state transition function that changes states as it processes symbols and then recognizes a string and therefore a language, which is a set of strings that it recognizes. So more specifically, a finite automata is a set of states, Q0 through Qk. Usually they're represented as ovals like that, as circles. Transition function delta takes you from a state and a symbol to another state, and that's denoted by an arrow between these two states. So Qi takes you to Qj if you see a particular symbol, and I usually use blue to denote a transition function, so the arrows will be blue, delta will be blue, set of states will be green, the initial state will be Q0, it'll be purple. So I'm color-coding everything for you to reinforce what corresponds to what in these pictures, to be extra intentional about what means what and what corresponds to what. Okay, so the initial state is one of the elements of the set of states. So Q0 is an element of Q, the green total set of states. There it is there, right there, the first one, without also generality, is taken to be the initial state. Why the initial state? Because you got to start somewhere. Computation starts somewhere. It doesn't start nowhere or in some arbitrary place, right? There's the initial state of a computation that then starts evolving, and then finally you may end up in some final state. And when you end up in a final state, you accept whatever it is you were being given to as input. Otherwise, you reject. So computation outcome is either accepting or rejecting. There's no other outcome. Okay. Now, the set of final states is a subset of the set of states, not a single state like here, an element of, but a set of, subset of. It could be all of them, could be none of them, or it could be one or two, or any number of them. Any subset could happen as a set of final states. Because you got to start in a particular unique single place, but you can end up in many places, not just one. Okay. The finite automata is therefore the quintuple, the 5-ordered tuple, the set of states, the alphabet, the transition function, the initial state, and the set of final states. Together, that completely defines the finite automata. So for example, the finite automata that accepts all odd-length strings of zeros will look like this. Here's the initial state, purple, Q0. You start here, that is a little caret, a little arrow going into it. That denotes the initial state. I'm also using purple to denote it yet again, twice, as the initial state. Also, the Q0 usually means the initial state. So it's denoted 3 different times as initial. Purple, 0, and arrow into it. So there's no way to confuse it with any other state. And then if you see a 0, you go here. You see another 0, you go there. This is an initial state, but not a final state. This is a final state. So the only way to end up in a final state when you process all the input is if you have an odd number of zeros. So 1 0, 2, 3 zeros, 5 zeros, 7 zeros, 9 zeros. But if you have an even number of zeros, you'll end up here. And when you reach the end of the input, you stop. And whatever state you happen to be in, that determines whether you accept or reject. Okay. So the total machine that's depicted here as a picture is given here more symbolically as this 5-tuple. How do you know it's a 5-tuple? 1, 2, 3, 4 commas separating 5 things. What are those 5 things? A set of states in green, color-coded green, right? The alphabet is only a 0. That's an easy one. And then transition functions, that's where all the action happens of how the machine operates. And finally, the initial state, Q0, and the final state, set, Q1, taken as a set. Now, what is this initial state? the initial state is Q0, and the set of states is Q0 and Q1 together. And again, I'm color coding it for you, purple and red, right? Purple and red, arrow and double circle to reinforce that even more. And here's a transition function. If you're in a state Q0 and you see a 0, you go to Q1. That corresponds to this arc here. If you're in Q0, you see a 0, you go to Q1. That's this blue arc right here. The second one, if you're in Q1 and you see a 0, you go to Q0. That's this arc right here. Okay, so these two transitions in blue are represented in these two pairs or tuples, where the first pair is a state and a symbol, and then the second element of the pair is which state you'll go to next if you were in this first state and you saw a 0 at that moment. This matches this type. This type of the transition function blue, again, blue, 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 the delta, the transition function, takes you from a state and a symbol to another state. And sure enough, state, symbol, another state. So all the types match here, as they should. They better match. If you have type mismatch or type errors, you're in trouble. Okay? Just again, I'll say what I said before. Be very careful about the types of objects. If you lose track of the types, you have no idea what the objects are. Right? If you don't know something is a mammal, you have no idea that it's a zebra. Right? Even if you know it's a mammal, it may or may not be a zebra, and you may not be sure. But if you don't know it's a mammal, it could be a vegetable or mineral, not necessarily a zebra, or not even an animal. Right? So be careful about types. Make sure you know the types. If you don't know the types, you have no idea what the object is. And most of you, and occasionally myself on rare occasions, will make type errors. Try not to do that. Any thoughts, comments, questions about any of this? So we defined finite automata. It's an abstract machine model. It's the simplest one that's not trivial that we know of. In fact, it's really the simplest one you can think of because there's not a whole lot going on here. There's a bunch of states and a few transitions. And some of the states are designated as initial and final. That's about it. That's all it is, really. But you can do a lot still. We're about to start exploring what this computation model can do, and also what it can't do. Okay? So you consume symbols as you go, beginning with the initial symbol of the input. You transition every time you consume another symbol from the input string. By the time you get to the end of the input string, whichever state you're in, accept or reject, is when you accept or reject the string. And the acceptance must always end up in the final state, otherwise it's not an acceptance. Rejection is anything else, including hang-ups or crashes. So for example, let's accept all strings of the form AB, 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 and so on, which really is AB star. So AB star will be accepted by this machine here. You start at the initial state, Q0. If you see an A, you go here to this non-accepting state. You see a B, you go back to the initial state, which is also an accepting state. So as long as you see an A and a B any number of times, you will accept, otherwise you will reject. Here's the formal definition. And this will accept this language, A, B star. How many understand that? Okay, any questions about that? Because it can sometimes crash on a string. Right? So for example, if you're in here and you see an A, you have nowhere to go. But if you're here and you see an A, you just saw an A, that's how you got here. And if you see another A, it's not a string of this form, that means there's two A's in a row. So you should not accept, and this machine will hang or crash. But remember, a rejection is anything other than acceptance, including crashes. So if you crash, you implicitly reject by virtue of not accepting. It's like a passive way of rejecting. Okay. Now, if you don't like crashes, and most of the time crashes are not great, usually it means you forgot something or didn't account for some error condition or some series of events that you didn't take into account in the logic of your program or your machine or whatever. You can always augment a finite automata to never crash. The way you do it is in places where you have a state and a transition that was not accounted to before, create a new state, a dead end state, a garbage collection state, where you're in here and you see an A. Instead of crashing, go here, and then if you see an A or B, stay there and never go anywhere else. There's no arrows out of this state back to the rest of the machine. So you'll end up there, you'll stay there, you'll never accept, you'll always reject, but you won't crash. You'll just now gracefully reject by consuming the rest of the input, staying there, not accepting, because that's the only accepting state, and you're good. Similarly, if you're here and you see a B, before you would have crashed. Now you go here and you don't crash. So that's like augmenting your program to take care of all the exceptions and doing something graceful, including possible termination, but doing it without crashing, without going array out of bounds or some hard error. You don't want to crash if possible. Any questions about that? Yeah.
Does that accept a single A?
Good question. Does it accept a single A? You start here, you see a single A, you go there. That's the end of the input. So now you're there and you're done. And so this is not accepting state, so you don't accept, so you reject, so it will not accept the A. And it shouldn't accept the A, because it should only accept strings of this form. And A is not one of those, because there's no B after the A. Right? So it does the right thing for an A. Any other thoughts, questions, comments? All right. Now this may seem kind of a simple model of computation, and it is one of the, it's really the simplest non-trivial model of computation that we know of. But very quickly you'll see that this kind of model can do very subtle things and have all sorts of interesting behaviors and theorems about it, and we're getting to that very quickly. So a transition function extends from a single symbol. You can extend it to arbitrary strings by inductively applying it to itself multiple times. So the transition function, when you start with Q0 on some string W and a character X, is the same as applying delta to itself on a Q0 with a W, and then whatever state comes out of there, you then apply delta to it and finally the X. So this is the inductive definition of how you extend delta from individual characters to whole strings. It's just an inductive definition where the base case is delta of Qi with seeing an epsilon, that is no characters, you stay there at Qi. In other words, you do nothing. And the language of the machine, we already mentioned that, but here it is formally. The language of the machine, this finite automata, whatever finite automata you might have, is all strings in sigma star such that delta takes you from the initial state based on that string, you end up in a final state when you can completely consume that string according to this inductive definition. And so it's basically all the strings that will cause the machine to go from an initial state to some final state and accept all such strings, not just some of them or your favorite ones, it's all of them. That's the language of the machine. It's whatever the totality of strings that it accepts and none of the ones that it rejects. Okay? Now here's the first definition about finite automata, other than what they look like. The language that a finite automata accepts is called a regular language. Again, a regular language is simply a language that's accepted by some finite automata. Which one? We don't care. As long as there exists one that accepts that language, it makes that language regular. You'll see later why we chose the word regular. It has to do with regular expressions. It'll turn out those languages accepted by finite automata will coincide with the languages expressible by regular expressions. Precise correspondence, interestingly enough. Okay? So, first theorem about finite automata. Complementation preserves regularity. If you take a language and you complement it, take the complement of the language, that is sigma star minus the language. If that language was regular to begin with, the complement must also be regular. If there's a finite automata that accepts the language, there's also another finite automata that accepts the complement of the language. That didn't have to be the case. Some language classes that we'll see later are not closed under complementation. The language will be of a certain type, but its complement is not of that type. We'll see examples of that later for other classes. For finite automata, that happens to be true for regular languages. And here's how you prove it. You take the machine like this one here, and you just negate the final and non-final states. You flip them. So a final state will become a non-final state, and a non-final state will become a final state, and a non-final state will become a final state. The transition state is the same. But this machine will do the opposite of what this machine is, the contrary machine. It'll operate exactly like the original machine, but when this machine makes a decision like accept here or reject both of these places, it'll do the opposite, reject here and accept in these other two places. So by flipping the final and non-final states, you negate its behavior to do the opposite of what the original machine did or did not do. How many understand that? Okay, any questions about it? So through this example, we basically prove the theorem, because you can do this for any machine you want. You can always create another machine and flip it by negating the final and non-final states. So essentially, it's a proof by simulation. This new machine simulates the old machine and then does the opposite. Right? Flipping the answer. the single bit that's the answer. Now, before you do this, flipping, I should say that this machine has to be fully specified. It should not hang anywhere. Because if it hangs somewhere on some input and you try to flip a hang, you're going to get into trouble. And it may not end up being the complement machine. So the machine better be fully specified and nowhere hanging before you pull this stunt of flipping the final non-final state and expecting to get the exact complement of the original language. So it's a little bit of a caveat, but you can always do that. Whenever the machine wants to hang, just make sure it goes to some garbage state that makes it reject without hanging. That's always possible. Okay? Any thoughts about any of this? Comments? Questions? Okay. Because these theorems will get more and more less, non-trivial, put it that way. Yeah.
You need to ensure determinism.
Yes. So you can only do this to a deterministic machine. If the machine is not deterministic, we haven't talked yet about non-determinism. We're about to in 20 minutes. But when you have a non-deterministic machine, you can't flip it like that. And we'll talk more about that when we talk about non-determinism. But the bright side, you can always take a non-deterministic machine and convert it into another deterministic machine that does the exact same thing, and then you can flip that. So that's not a showstopper, the fact that you can't flip a non-deterministic machine. First convert it to a deterministic one, then flip it. Now you got the complement of that. Yeah.
Does this apply to any machine if it is deterministic?
Yes. So this applies to any finite automata. Now, it doesn't apply to Turing machines or other things.
Even if it ensures determinism?
So when it comes to other machine models, it's non-determinism would be essential to the model. So for push-down automata, non-determinism cannot be simulated deterministically. So non-determinism is hard-coded into the definition, and it's there in an essential way cannot be made deterministic. So you cannot just flip a PDA, a push-down automata, a stack automata. So this doesn't work. In fact, the context-free languages are not closed under complement as a consequence of that. We'll talk more about that when we get to it. So some classes of languages are closed under complement, some are not. This one is, the regular languages. Yeah.
So what does it exactly mean when you say the invert of the automata is doing the opposite of the original? Like, for example, the first one accepts A, B, A, B, A, B.
Yeah.
And does the second one accept B, A, B, A, or?
Well, so A, B, A, B, A, B, and you end up here and accept. Here it'll be A, B, A, B, A, B, end up here and not accept.
Oh, okay, I see.
So it does the opposite because the states are flipped. The final and non-final sets are flipped. This was final, not final. Not final, not final, final, final. So it accepts exactly sigma star minus the language. So if a string is accepted by this, it won't be accepted by that. If a string is not accepted by this, it will be accepted by that. And it's an if and only if. So a string will be accepted by this if and only if it will not be accepted by that. In other words, this machine does the exact opposite. It recognizes everything but the string is accepted by the first one. So it accepts the complement of the language. Okay? So it's kind of a contrarian machine. It does exactly what the first machine doesn't do in terms of accepting and rejecting. Any other questions, comments? It's good that you're asking all these questions because we should clear up all these issues now before we get into deeper water. Right now we're in very shallow waters here. We're not that far from the definitions right now. Soon we'll get into deeper, trickier situations. So in terms of to go deeper into your question, so the first machine accepts AB star. The second machine, how do you break this rule that if you have AB, AB, AB any number of times as long as it's an AB pair repeated any number of times? How do you break that rule? Well, this one starts with an A and ends with a B, no matter how many ABs you have. So you can either start with a B, and that breaks that rule, or end with an A instead of a B, and that breaks that rule again, or have two A's in a row and two B's in a row with anything before and anything after. So this is sigma star AA or BB and then another sigma star. So the strings that are not of this form are either strings that begin with a B, end with an A, or have a double A or double B in them somewhere. And that's all there is in the complement of the language, strings that break the first rule. How many get that? And this complement machine M prime accepts exactly this language represented as this bigger regular expression. So these two regular expressions represents the complements of each other. Each one is the complement of the other. By the way, the complement of the complement is what? It's itself. The complement of the complement of the language is that language. Question? Yeah.
So the AB star is a regular expression. It wasn't that Kleen function or the one before,
So
right? Because that would be any combination of A and B.
yeah, so remember the language is the language earlier in the previous slide is any number of AB, AB, AB repeated as many times as you want. That's really AB star. And the complement of AB star is this expression here. Now, as a pedantic type error kind of issue, don't say that the language is AB star. That's a type error. What should you say instead? Let's see if you're up on your type error, checking as you speak. If I say, the language of this machine is AB star, why am I making a type error? Yeah. What else? What's the ambiguity? Where's the type error here?
It starts with A and B star.
No, it's more fundamental than that. So if I say the language of this machine is AB star, and I'm telling you I'm making a type error. Where is the type error?
AB star is a string.
What is AB star?
It's a regular expression.
Is it an animal, mineral, or vegetable? What type of object is it? It's an expression. It's a regular expression. A regular expression is not a language. It's not even a set. It's a formula or an expression that denotes a language, but it's not the language itself. How many get this subtlety? Okay, so be careful when you speak of these things. Do not make type errors. So the language of that machine is not AB star. The language of this machine is the set of strings denoted by the regular expression AB star. It's like saying, there's the corridor, this is the corridor. But this isn't the corridor. This is a door that will lead you to the corridor if you step through it. Okay? And I'm not just being overly pedantic here, because these types are pretty straightforward. But later, we'll have types that are so nested and convoluted, you wouldn't even know what the type is, much less what the object is that we're talking about that has that type. Right? You wouldn't even know if it's a mammal or not, much less if it's a zebra. And you will all make these errors left and right, I assure you of that. How do I know that? Because I've been teaching this longer than you've been alive, and it happens every single semester repeatedly. And just to test this, what's the type of 2 to the sigma star? We mentioned 2 to the sigma star. 2 to the sigma star is a set. But let's go deeper. It's a set of what? Set of sets. And each one of these sets that is a set of is what type? Let's go all the way down to the bedrock. Like, basically unroll the type completely. Finite set? So let's say sigma is A comma B. 2 to the sigma star is of what type? See, you're already having trouble with types. And we just dipped our toe in the water. We're not even in deep waters yet. Set of languages. And what type is a language? Set of strings. And what type is a string? You see? That's exactly what I'm talking about. You're not sure what the types are. That's exactly what I told you would happen. And we're still in very, very shallow waters here. It'll get much more convoluted later. All right, so let's keep nailing it down. 2 to the sigma star is of what type? Sets of alphabets? Strings, but a string is a set of what? Or is it a set? I don't want to put words in your mouth. What is the type of a string? A string is, it's not a primitive, it's not an atomic.
Concatenation of symbols.
It's not atomic. Yeah, a string is a sequence of symbols. Symbols are atomic. They're like the elements. Strings are like molecules. Right? And then languages are like compounds or alloys or whatever you want to, however you want to think about them. So 2 to the sigma star is what? Say it once, say it correctly, and go all the way to the rock, to the rock bottom of the atomic definitions. A set of sets of sequences of symbols. Bingo. Now you got it. 2 to the sigma star, its type is a set of sets of sequences of symbols. The type is nested 4 deep. We good on that? That's why it was hard to say it. It's not just a type of something. It's a type of a type of a type of a type, nested 4 deep. 2 of them were sets, 1 was sequences. What's the difference between a sequence and a set? 1 word. Order. Right? A set is unordered. A sequence is ordered. Big difference. And you'll run into occasions where the sets will be even more convoluted than that in type, and you won't even have any idea what the type is anymore. Unless you think about it really hard and nail it down, and only then you'll have some chance of knowing what the object is, never mind its type. This will happen again and again. I just showed you an example where it actually happened. Okay. Any other thoughts so far? All right. All right, so another example. Design a deterministic finite automata, DFA, that accepts all strings where any A's are preceded by any B's. Any A's precede any B's, rather. So the idea is you can skip over the A's when you start, and then when you see a B, flush all the B's. And if B's is all you see after the first B, then accept. But if you see any A after one of the B's, then end up here and reject. And it's a fully specified finite automata. It accepts this language. And this language happens to be equal to the language denoted by the regular expression. Notice I'm using types very carefully in my speech. A star, B star. Right? Any A's precede any B's in any number. So if there's no A's, that's okay. Start here, see no A's, go right here on the first B, and then see a bunch of B's, and you're still good. So it is A star, B star. It's not A plus B star. Okay? What is the complement of this language? Well, the complement of this language is when some B precedes some A. Because the language definition is all A's precede all B's. So if some B precedes some A, you have to have at least a B here, B plus, and at least an A here after the B, A plus, and in between them, before them, and after them, sigma star, anything goes. How many understand that? That's a complement. That's breaking that rule in every possible way. Of course, if you see any number of B's followed by an A, somewhere you would have a B, a single B preceding an A, and that's enough, so you don't really need the plus here. And if you have a bunch of B's, then followed by a bunch of A's or B's, and then followed by an A, that's some B preceding some A. If a B eventually becomes an A, it'll become an A in one step, somewhere in between. How many see that? And that's why I can eliminate the sigma star in this middle. And eventually, there'll be a single B before a single A, and you might as well have the first occurrence of a B becoming an A as opposed to an arbitrary occurrence. And so you see these regular expressions become smaller and smaller and still represent the same language. So I'm putting equality signs between them, denoting that they represent the same language. The language hasn't changed. The regular expression became simpler and simpler until we had A star, B plus A, and then anything you want after that. How many understand that this all represents, all these regular expressions represent the same language? They just become smaller and smaller. Now, in general, it's hard to minimize regular expressions. In fact, we know of no efficient general algorithm, polynomial time algorithm, to minimize regular expression. We don't know if it's possible to do in polynomial time. It's an open question. If you can do that, then one of the implications will be P is equal to NP, for example, or some such interesting result like that. But that's an aside. So this gets you a bunch of A's, the A star, then a B, as many B's as you'd like. That's a B plus right here. And then finally an A and whatever else you'd like. Notice that this machine is the complement of the previous machine that we had here. Looks exactly the same, except we flip final and non-final states. Final, final, non-final, 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 final. We flip them. So it kind of makes sense even with respect to the, and it makes sense with respect to the regular expressions. So we kind of solved it twice. Any questions about this example? So you see, it's not trivial to convert a regular expression to a finite automata in a little bit. Probably today even, we'll see a mechanical way of doing it that always works no matter what. But coming up with a minimum finite automata is a trick. And coming up with smaller regular expressions that still represent the same language or denote the same language, that's an even bigger trick. Of course, such a regular expression exists always that's minimal. How many understand that? You know, because of all the regular expressions in the universe, there's the smallest one, least number of characters. It represents a particular language, right? But it's hard to find it necessarily. It's not easy to find, but it does exist. Now, you could always minimize a finite automata to the smallest number of states that still will do the same job as the one before, the bigger one. That one is not hard to do. In n log n time, you can always minimize an arbitrary deterministic finite automata to the smallest possible number of states. It's called a state minimization algorithm, and it works in n log n time. And Hopcroft and Ullman back in the 70s gave this algorithm in the very early 70s. All right, there's a finite automata workbench / compiler or programming environment called JFLAP. How many have actually used it before? JFLAP, okay. So I want you to use it to implement certain finite automata in the second homework that's already posted. There's a couple exercises that just take you in JFLAP and have you implement a couple of simple finite automata and test them and run them on certain strings and then submit the screenshots. And it's a nice way to implement them, test them, debug them, make sure they work, and see how they operate. And I want you all to use that. Of course, well, you have to use that if you want to do the second homework, which is part of the grade. So you will be using this, and it's a good thing. Just like when you write code, you don't just write a piece of code on a piece of paper and walk away and say, I got it, without compiling and testing it and running it. That would be kind of silly to just say, oh, this is correct. I know it's correct. I'm not going to bother running it because I know it's correct. You would never do that with code, and you shouldn't do that with finite automata or Turing machine or stack automata or any one of these constructs in this course. You want to test them, run them, implement them, test them on a bunch of input strings, see how they work, see how they state change. The states are highlighted as it executes. You can single step, or you can run it to completion or whatever. It's a very nice way of testing your finite automata. Here's some more screenshots of examples of how this tool works. And this tool not just handles finite automata, it also handles Turing machines, push-down automata, grammars. You can do operations on these objects. You can convert them from non-deterministic to deterministic. You can minimize the number of states. You can convert grammars to other grammars, and all sorts of interesting theoretical constructs implemented there in this workbench. You can also do fractals and Lindenmayer systems, and it has a bunch of different things going on. Okay. Any questions or thoughts about this? So by say next week, I want you all to have practice with this as part of your second homework assignment. So in the book, this brings us to roughly page 40, 45, roughly, and now we're about to show some closure properties for finite automata. So first closure property, the regular languages, they're closed under intersection, under set intersection. Remember, a language is just a set of what? A set of strings. A string is a sequence of symbols. So a language, its type is a set of sequences of symbols, right? So if you take one language, intersect with another language, these are set operations, right? On sets, a language is a set, right? So you can apply intersection, union, complementation, set difference. Any operation you can apply to sets, you can apply to languages, because languages are sets. They're a special kind of set. So anything you can do to sets, you can do to languages specifically. So intersection preserves regularity. What does that mean? It means if you have two languages that both are regular, if you intersect them as sets, the intersection is also regular. Another way of saying it, if there's a finite automata that accepts the first language, a finite automata accepts the second language, there's a third finite automata that accepts the intersection of the two. Okay. It's not obvious. And for some language classes, it's not even true. It happens to be true for regular languages. It's not true for context-free languages, which we'll talk about in a couple of weeks. But it's true for regular languages, that intersection preserves regularity. How do you prove such a thing? Well, you can do it by simulation, for example. So let's say you have two finite automata that accepts two languages respectively, and you feed both finite automata the exact same string. Never mind what it is, call it W. You feed the two finite automata the same. So first finite automata, execution on W, represented here in this sequence of state changes. The second sequence of state changes is the execution of the second finite automata on the same string W. So these two state sets are not the same state set. They come from two different machines, right? So this Q0 is not the same as that Q0, but they're both initial states. This final state is not the same as that final state, but they're both final states in the respective pair of machines. Okay. So how do you construct a finite automata that accepts the union of the two languages accepted by these two machines respectively? Again, I'm being very careful in my words about types. How do I do that? Well, I construct so-called superstates that are composed of pairs of states, one from each machine respectively. So this pair of states here together will become a superstate, a pair of states. This pair will become a superstate, and so on. Now I'm going to define in my super intersection machine super transition function in blue, color-coded, that will jump from one superstate to the next if the two component states of that first superstate respectively in the two machines ended up, for that character of the input, in these two resulting target states in the two machines respectively. And if that's all true, I'm going to have this first superstate jump to the second superstate on the same character of these two transitions individually. Because remember, we're talking about the same string W fed to both machines. And now this same string is fed to the super machine that simulates what both machines are doing in parallel simultaneously, like two threads. How many see the strategy here? What's happening? Not a single person. Oh, okay. Perfect record. All right, I'll repeat. This execution is execution of the first machine, and the second execution is execution of the second machine, both for the same input W. Which two machines I'm talking about? The two machines whose language I'm going to intersect. Why am I doing that? Because I want to prove that the intersection of two regular languages must yield a regular language, not some other non-regular languages. There's plenty of those. There's actually an uncountable number of non-regular languages. So I want to show that regularity is preserved by the intersection operator. So that means if I have a machine that accepts a language, another machine accepts a language, there's a third machine that accepts the intersection of their two languages. And it's not obvious that this is always true, except it happens to be true, and we're about to prove it. So I'm going to take this first machine that accepts the first language, and the second machine accepts the second language, and executes them both on the same input string W. Right? Now, here's the initial state of the first machine. This state of the second machine is not necessarily different than this. A lot of these states along the first path could be the same as one another. How many understand that? They could be represented there multiple number of times. So I'm not saying these are all different states in the first machine, because it could be cycles, and it could be the same state over and over again. The machine can have two states, so this is the same as this, the same as that, and that's another one. It's the same as this, it's the same as that, and that's maybe a third one. So I'm not saying all these states are different. I'm representing them as different circles, showing you the path of execution of the first machine on W, and separately showing you the path of execution of the second machine on the same string W. Okay. Now I'm going to define a hybrid machine, a super machine that will have superstates, and the superstates of the new machine will be pairs of states, one coming from each of the two machines respectively. Right? So each pair of states, one from each machine, will constitute a superstate, a pair of states in this bigger machine that I'm constructing for recognizing the intersection. And what is the transition function on these superstates? Well, one superstate will be transitioning to another superstate if and only if the first component of the first superstate will transition using the transition function for the first machine into the first component of the second superstate. And at the same time, the first component of the first superstate will be transitioned according to the transition function of the second machine to the second component of the next superstate. And if both of these conditions are true, I'm going to transition this superstate to that superstate in one jump. So this transition here in blue represents two transitions in the two machines respectively that happen simultaneously on the same input character, one of the symbols in W. How many get it now? Good. I'm glad I asked. I'm glad I explained it again. Okay, so this transitions in big arcs from superstate to superstate is the transition of the new super machine jumping around on superstates, doing the work of both machines simultaneously. It's like running two threads in parallel in your operating system or in your iPhone or whatever it is in your program. Right? It's like parallel simulation, if you will, right here. So the initial superstate will be the pair of initial states from the two machines respectively. It will be the initial pair of the initial state of the first machine and the initial state of the second machine taken as a pair, which will be the superstate, initial state of this super machine that I'm constructing, the intersection machine. And what are the final states of the super machine? Will this be a final state? Will this be a final state? Will this be a final state? Yes. Why this and not these two? Because it's the intersection. Intersection means and. This has to be true and this has to be true. It has to be in this set and in this set. So this has to be final and this has to be final. If one of them is final, the other one is not, it's no good. That means it's not accepted by both machines. It means one machine accepts and the other rejects, or one rejects and the other accepts. Both have to accept for this superstate to be final. That's why I circled this one is in red. Okay, maybe to be consistent, I should circle this in double big square red. But still, it's good enough. This is a final state and not these in the super machine. Okay, so the resulting deterministic finite automata that I've constructed accepts the intersection of the two languages accepted by the original two machines from which I constructed this, right? So in terms of symbolism, here's what's going on. So the first machine, call it Q1 sigma delta 1 Q naught F1. So F1 is the final state set of the first machine. F2 is the final state of the second machine. Delta 2 is a transition function of the second machine. Delta 1 is a transition function of the first machine, and so on. So here's the two machines defined, symbolically. So I'm going to construct a new machine M, whose Q is the cross product of the two state sets Q1 and Q2. How many understand that? I'm crossing the two state sets of the two machines, resulting in these super states, pairs of states. Okay? And the final state set of the new machine F is the cross product of all final states from the first machine and all final states from the second machine. Taken in all combinations, that's what the new final state set is. And there could be a bunch of those. Right? The initial state, again, color-coded in purple, the initial state of the hybrid simulating intersection machine is the initial state of the first machine, Q prime, and the initial state of the second machine, Q double prime. It's right there, color-coded purple. All right? And the transition function basically takes us from a pair of states, Qi, Qj, a pair of states, on a particular symbol of the input, to whatever the initial transition function of the first machine took us to, comma, whatever state the second transition function of the second machine took us to from its second component of the state on the same symbol x. So this x is the same as these two x's. Right? Here's the transition function of the first machine, the second machine. So it's this one and this one. And this transition function will take us from here to here. Right? So formally, the transition function of the new machine does the same job of both transition functions of the two machines, respectively, from which we constructed it. And you get the intersection machine, the cross-product machine. Okay, how many understand this strategy, this schema, this proof? Okay. Any questions here? Yeah.
So this is a minimized version of the example that you've given?
It's not necessarily minimum.
Because we have Q, which is the cross product of the states of Q of M1 and M2.
When you say minimum, you mean the least number of states?
Yeah.
No, it will not minimize the states.
Because they haven't represented all those.
So you have to be careful. First of all, the original two machines may not be minimum. The original two machines may be way too large than they have to be.
No, I'm just asking the example.
Oh, you mean
The example.
the example right there? It's not minimum.
We've not represented the states which are, let's say, for example, Q0 of the first one and the Q1 of the second one.
Oh, one of those can be that. So this is Q0 of the first machine. This could also be Q0. This could also be Q0. A lot of these could be the same Q0. So a lot of these states here along this path could be repetitions of other states, including Q0. Does that make sense? So just because I represented 1, 2, 3, 4, 5, 6, 7, 8, 9 states along this path, doesn't mean they're all different states. It could be the same single state repeated 9 times.
I just feel that the mathematical representation does not represent the explanation.
Okay, I think it does. So let's try to resolve it. So why do you think it doesn't?
So the set of all states Q should be the cross product of Q1 and Q2.
So that's right here.
So which is not represented in the image.
Well, so the image represents an execution on a particular string of 9 characters long, on a particular W. This doesn't represent the execution on all possible strings, just one. So this is a very, very specific execution on a very particular specific string that I chose out of thin air to make this example in this picture. This is general now. This one isn't. Right? So in general, this 1, 2, 3, 4, 5, this 6th oval here will not necessarily be a final state in general. On this particular W that I'm not even writing down, it happens to be a final state here, non-final states there. But that's just very, very esoteric, specific to that W that I chose arbitrarily. In fact, I'm not even showing what the 2 machines are specifically. Never mind what W is specific. So this is a very specific picture. This is a very generalized notation. Okay. Now, this picture is general enough to illustrate the point of how superstates transition into other superstates by pairing them up like this. It's general enough to do that. And showing you that when two of the substates are final, are red, then the superstate encompassing them is also final and red. It's general enough to illustrate those points. But other superstates here could be red too, or none could be red. Or none could be final at all in any, or whatever. I mean, but then this picture will be even less general than it, than it already isn't general enough for the general case. So this is kind of a specific picture. This is the generalized situation down here. Any other thoughts or questions? Yeah.
I was wondering the cardinality of the intersection.
Yeah. So this is called the cross-product construction. It's a very generalized construction. And the reason it's called cross-product construction is because we're crossing the 2 machines together. We're crossing their state sets. So the size of this new crossed machine, this hybrid superstate crossed machine, could be how big as a function of the 2 sizes of the 2 original machines, respectively. How big? The product of their sizes, right? And by size, we mean the number of states in it, right? So the new machine can have as many states as the product of how big the other original 2 machines were. So if one machine has 5 states and the other machine has 7 states, this hybrid cross-product construction machine could have 5 times 7 or 35 states. And that's a lot. So it kind of blows up quadratically, if you will, in the sizes of the 2 machines, assuming they're roughly the same size. Now, as a matter of practice, not all these superstates will actively be reachable in the new machine. How many understand that? Some of them will kind of be dead states, like dead code. Sometimes you have a huge program with a bunch of subroutines and never get called. You might as well remove those subroutines from your code, and code will operate exactly the same as it did before if those subroutines never get called. There's no call to them anywhere else. It's just dead code, unreachable code. Some of these superstates, if you just cross them together like this, some of these resulting cross states will be unreachable. You might as well remove them. But the largest the machine could be is the product of the 2 original machines. That product can actually happen. There are examples, our worst case examples, where it's exactly equal to the product of the 2 machines. Even if you try to minimize it after the fact, it'll still remain that size. That will be the minimum machine, the product of the 2. But it's rare that that happens. Any other thoughts or questions? So it's an interesting technique. We'll use it a lot. In fact, we'll generalize it very soon. In fact, certainly today, to something called the power set construction, which is a generalization of this. Bottom line is the intersection operator preserves regularity. If you have 2 machines that accept two languages, there's a new machine that accepts the intersection of those 2 languages. Right? Now, it didn't have to be this way, and for some machine classes, Push automata, for example, intersection does not preserve context freeness, but it does preserve regularity. Okay. Now let's quickly prove a bunch of other theorems in quick succession. So we're going to prove that the union preserves regularity. How do we prove that the union preserves regularity? Well, you tell me from this slide, if we see some intersection, you want to prove that the union is preserved as a regular language. Let's have somebody else who hasn't spoken yet today. I want to get more people. I don't want to call on people and put you on the spot, but I'm impressed with the same 3 or 4 people that keep answering my questions. But there's over 20 of you in the room, so I want to give others a chance to speak. Even if you're not correct, that's okay. You still have points for courage for speaking up where everybody's afraid to talk. So either way you win, no matter what you say. So how would you prove the union preserves regularity, not the intersection, with a very similar proof to this? It's almost identical. What's the only difference? Yeah.
Change the and to or.
Okay, and what effect does this have here?
So either one of them in the state, you will proceed to the next state.
So the final states in this machine are states where both of them are final, both components are final in the original machines, and that makes the pair of states final in the hybrid super machine, right? And that gets you the intersection. But to get the union, she's basically saying it, but somebody kind of paraphrase it. Either one of these is accepting will make this a final state. So not both, but one or the other or both, that will get you the union. Because the union is if it's in either set or the other set or both sets, that's okay, it's still in the union. To be in the intersection, there's not so much freedom to be in one or the other. You got to be in both. That's more constraining. So the intersection is always smaller than the union. It's a subset of the union, right? Sometimes it's equal to if their sets are identical. Question?
Can't we just, if you do the same construction, then it becomes a cross-product-based construction, and therefore n times m. So isn't it, you can reduce it to n plus m if you have a transition with one single.
He's asking an interesting question. He says, can't you execute one machine on the input, then execute the other machine input, and then see if they both accept? You got to do it in parallel, not in serial, because.
I'm not talking that way. So
Okay.
you have one initial state before that, and have a epsilon transition to.
Oh, sure. But now you have a non-deterministic machine. Yeah. So he's showing a non-deterministic construction for the union where you branch into both machines simultaneously with an epsilon transition from a new start state, and then you execute in one or the other in both. Yeah, that will work too, actually. But that gets into non-determinism, and remember, we haven't discussed non-determinism yet. But that's an alternate proof if you allow non-determinism. Yes, absolutely, yeah.
I feel like the intersection or the union you're talking about regarding the finite automata is more similar to the inner join and outer join in the SQL database.
Yeah, sort of. Yeah, you can think about it as kind of merging two tables or whatever, along rows or whatever. Yeah, that's an interesting analogy. Yeah, it's okay. So the proof for the union is very similar to the proof for the intersection, except the only difference is right here. Okay, so the union, you can prove it using the original, or you can prove it much more simply using De Morgan's law, which is a second alternate proof. So we already proved it the hard way at the previous slide, converting the intersection to a union and modifying that proof. But now let's prove it using De Morgan's law. So the union of two sets is the complement of the intersection of the complements. How many buy that? How many understand that? Yeah, that's just De Morgan's law for set, union and intersection as opposed to and or, right? Because the union and the intersection are defined as or and respectively, right? Union is or and intersection is and, if you think about it, with respect to set membership. So we already know that complementation preserves regularity. How do we know? What's the proof that complementation preserves regularity in one phrase? Flip the states or invert the states, right? Final and unfinal, flip them. So complementation preserves regularity, and we know that intersection preserves regularity. How do we know that intersection preserves regularity? Two words. Parallel simulation, or what's the proof technique called? Cross product construction, same as parallel simulation. Cross product construction, same thing. So the complementation preserves regularity, the intersection preserves regularity, and there's another complementation. So if L1 and L2 are regular, we're hitting them with all these operators that preserve regularity, but once we hit them with all these operators here, it's equal to the union. So the union must preserve regularity because it's equal to the other thing, and regularity is preserved on the right-hand side, so it must be preserved on the left-hand side because the left-hand side is equal to the right-hand side, so to have not just the same value, but the same properties, namely regular. How many understand this proof? There's only half the class. So let me repeat. We're about to show that union preserves regularity now that we know that complementation preserves regularity and intersection preserves regularity. How? By representing the union as the complement of the intersection of the complements. That's just the Morgan's law. It's a set identity. How many believe that set identity is true always for all sets? Yeah. Not everybody raised their hand. So is there an issue with the Morgan's law? Somebody want to dispute that? Or, I mean, it is called a law, so De Morgan was the illustrious logician that in the 1800s, mid-1800s, came up with that set identity, right? So once you believe the Morgan's law, if L1 and L2 are regular, then the complements of L1 and L2 are regular because of flipping final and non-final states. We already know that as a result, that complementation preserves regularity. So the complements of L1 and L2 are regular. If you intersect those two complements which are regular, intersection preserves regularity, cross-product construction from the previous slide. So the intersection of L1 and L2 complements, that's regular too. Now if you complement this one more time, that still preserves regularity yet again. So the whole right-hand side remains regular if L1 and L2 are regular. How many believe that? Okay, that's better. That's most people. And therefore the union is regular too because it's equal to that. So union preserves regularity, therefore, because it can be represented as these other operators which all preserve regularity. Okay. That's like saying that exponentiation is repeated multiplications, right? And multiplication preserves integerness. So if you have two integers, you multiply together, you get an integer. How many believe that? Okay. So exponentiation must preserve integerness too, because that's just repeated multiplication. Each multiplication preserves integerness, so exponentiation, which is just a bunch of multiplications all strung together, must preserve integerness also. The property is inherited through multiple applications of these operators that each preserve that property. Then this other property that's a composition of all these operators must preserve that property too, right? It has no choice. Okay, or you can do the cross-product construction. We already mentioned that on a previous. But instead of just highlighting all pairs of states where both are final, like we did before, we highlight pairs of states where either one is final or the other is final. Right? So the final state set is F is equal to all final state sets from the first machine with any possible states from the second, or any possible states from the first with only the final states from the second. And the union of those two are all the final state sets of the cross-product construction for the union, right? And in terms of picture, this becomes final, and this remains final. How many understand two different proofs here? Good. Which proof was shorter or easier, or more, or less likely to contain errors, glitches, oversights? Was it the hard core cross-product construction on the previous slide? Or was it just the Morgan's law? Just the Morgan's law, because the Morgan's law applies to any sets, in particular to languages, which are sets. And look how short it is, it's one line. It's hard for truth to hide here, and it's hard for errors to hide also in one line of reasoning. It's easy to have errors hide in a long, complicated construction. You have to wonder, does this work in all cases? Is it general enough? Is it some possibly weird exceptions to this technique that fail on certain cases? Or who knows? The answer is no, but it's not obvious. You have to think about it and scratch your head and eventually realize this is general, but it's much easier to see that this is even easier to see that it's general, De Morgan's law. So what I'm telling you is there's proofs and there's proofs, right? So we proved this union preservation theorem twice. Once using the hardcore method of the previous slide with the cross-product construction, but the cleaner, easier, simpler ways to prove it is using one application of De Morgan's law, clean, simple, straightforward, foolproof, right? Obvious. So always look for this kind of proofs. Remember the centrifuge problem and other problems, the staircase problem, sum of integers from the first lecture. Look for simpler, cleaner, more convincing, more concise ways to prove things if you can. Don't just go brute force, hardcore, and don't just be correct but complicated and obfuscated if possible. That's a constant theme that I keep harping on Occam's razor, right? Simplicity wins. Simpler is better. It's preferable. Okay, let's keep going with Occam's razor. Set difference. How do you prove that the difference between two languages preserves regularity? If two languages are both regular, the set difference of the two is regular too. You can use this hardcore construction. Which states here will be final if you're talking about the difference between two languages? L1 minus L2. Let's put it, will this be final? No. It's the difference. This got to accept, but this can't accept. If both accept, the answer is not in the difference. Right? Is this final? Yes. Is this final? No. So you know how to do this now. Same as the cross-product construction with this modification of the final state. Or you can use this set identity. That the difference of two sets is the same as the intersection of the first with the complement of the second. How many believe that the set identity? It's true. Right? You can use it, you know, draw a couple of ovals and show that, right? The difference between the two, let's just do it instead of talking about it. So the difference between two sets, A and B, where's the difference here in this picture? Right? The difference is here, you know, A minus B. It's everything that's in A but not in B. So this is excluded, this region here. So it's A minus the intersection of A and B, right? Or it's A intersect the complement of B, right? The complement of B is everything outside of B. Everything that's in A that's outside of B is this region again that I've highlighted, right? It's the same region here. So the difference is this, right? So there's a set identity, and now we know that complementation preserves regularity, intersection preserves regularity, and that's why difference preserves regularity too, because it's a composition of these other two operators. How many understand that proof? So it's proof by set identity. We don't have to go kind of hardcore cross-product construction again and argue from scratch, right? So you see now the final state set is the final states of the first machine crossed with all the non-final states of the second machine, Q2 minus F2. That will get you this state, but not that state. Okay, how many understand that construction? So that's a modification of the cross-product construction to have this hardcore, longer, complicated proof. XOR preserves regularity. Again, you can go cross-product construction on this theorem. XOR. Will this be a final state? Let me not be presumptuous. What is the XOR on two sets? Set 1 XOR set 2. What does that mean? Is it the difference? No. Not quite the difference. It's the
union minus intersection.
It's the union minus the intersection, right? It's everything that's in one and everything that's in the other, but not everything that's in both, right? It's got to be in one or the other, but not in both. That's the XOR. It's also a logical XOR on two truth values. One is true, the other is true, but not both are true. It's this XOR that, right? Another way of saying it's the union minus the intersection. But already the union minus the intersection, right there, we know that that preserves regularity. Why? Because intersection preserves regularity. How do we know? Cross-product construction. Union preserves regularity. How do we know? De Morgan's law. The difference preserves regularity. How do we know? The set identity. End of story. So the application of this operator, and this operator, and this operator, all of which preserve regularity, will also preserve regularity, but that's equal to the XOR. So the XOR preserves regularity too. QED, end of proof. So you see how quickly now we can prove more identities. Now we've proven one the hard way. We can prove a whole bunch more the easy way. And you can keep proving these things. There's lots of other identities you can prove. The operators, certain operators preserve regularity. How about NOR, not OR? The NOR of two sets. Does that preserve regularity? How many say yes? Yeah, sure. Just write this identity and it'll be done. And same for NAND, the NAND of two sets. You can say like the complement of the union, I guess is the NAND or something, or the complement of the intersection, I guess. So you see, we start applying other operators, you can quickly see that. And in terms of cross product, if you really wanted to do XOR and cross product, you'll say the final state set of the cross product is the final states of the first machine crossed with non-final states of the second machine, or non-final states of the first machine crossed with final states of the second machine, all union together. So just to be, complete and precise, if you were going cross product construction or parallel simulation construction on this theorem, you would define the final state set of the hybrid machine to be that, and you'd be done again. But that's the hard way to prove it. The easier way is just set identity. So the meta theorem here is that identity-based proofs are much easier than construction, hardcore, kind of basic notation, basic principles, kind of simulation kind of proofs. If you can muster it. Now, I'm not saying you can always pull an identity off, out of your hat and pull it off, but when you can, please do. Because it's easier, it's simpler, it's cleaner. It's very nice. Any other questions about how many understand everything on this slide? Okay, that's good. It's most of you. Any comments, thoughts, questions? And in the book, this comes from page roughly 47, 48, 49, and now we're about to go into non-determinism. And let's take a 10-minute break and get back to non-determinism and knock out that topic. At least with respect to finite automata. It's a very deep topic. You can have a whole semester just on non-determinism, but at least the initial round of non-determinism with respect to finite automata, we can talk a good hour about that and make nice progress. All right, so see you in 10 minutes, and we'll pick it up then.